Thanks a lot for inviting me. This is a wonderful meeting. I really like this. And thanks for sticking around. I'll try to finish in time. So this is joint work with Gergő. Well, I was spectating, assisting Gergő. He had the main idea, this, which is a really strange idea. I will try to explain this to you. So this is about classical statistical learning theory. So and the classical goal for statistical learning is to understand the generalization ability of machine learning algorithms, right? So we learn something using data, and the question is this going to work on future data, and if it does, why, and how can we certify that? Okay, so this has a long history, but of course we all know that now this deep neural networks, they shattered our worldview. Classical statistical approaches seem to be contradicted by the behavior of this. So this gave another big kick for this area. Try to understand. Why do these strange, complex, complicated algorithms generalize where we thought that they shouldn't? I'm not gonna solve this problem, but what we do is we present a new framework, which is based on online learning, and we think I will give you a few examples of to illustrate how this works, and I think that this has some future, and maybe it will give us a framework to understand the performance of the generalization abilities of complicated algorithms. So here's the setup. It's really simple. We have training data. These are IID, independent identically distributed random elements. You can think about vectors in RD. Our main example actually is you can think about linear, just regression, where the training data consists of pairs, x's and y's, and we also have a hypothesis class. Okay, so this hypothesis class is typically parameterized by some high-dimensional vector. You can think about hypothesis classes as neural networks if you want to think about something concrete of a fixed size. So that's our class. And for each neural network and for each data point, we have a loss. Okay, so you can think about evaluating the value of x for this neural network and comparing it to y and taking the squared. So that's the loss function. And the learning algorithm just takes data, takes independent random samples, independent identically distributed random samples, and outputs a hypothesis, outputs one of these W's. More generally, this algorithm can also use randomization, in which case the output is a probability distribution over the hypothesis class. Okay, so this capital delta just denotes the set of probability distributions over the class, right? If you use stochastic gradient descent, then you have intrinsic randomization of the algorithm that is important. So we want to frame this in this generality. Okay, and then Wn is the final the element of the hypothesis class that this algorithm outputs. Okay, which depends on the data. So if this is a random variable, it depends on the data, but it also depends on the possible internal randomization of the algorithm. Okay, so this is the learning algorithm, and what we would like to understand is the behavior of this learning algorithm. In particular, what we're really after is the risk, the expected loss of this learning algorithm on a future data. So this Z prime is an independent new future data. It has the same distribution as the training data, and we evaluate our algorithm on this new data. Okay. In statistical learning theory, traditionally focused on what's called the excess risk, which is the risk of what we learned from the data compared to the optimum over this hypothesis class. And it is the best we could do if some oracle told us the distribution of the data, and if we were restricted to choose a function from our class. Okay, so this is how much worse our algorithm does compared to the best possible algorithm in this class. Okay, so this has studying the excess risk has a long history. A beautiful major breakthrough came in the early 70s, I would say, maybe even late 60s, from the Soviet Union, Vapnik and Chervonenkis, who mostly focused on understanding this excess risk. These are our heroes. So what they showed is that is kind of what is the tightest possible way of understanding this in a distribution-free manner. So if I want upper bounds and actually lower bounds on the minimask risk, where we take the behavior of the best algorithm in the worst case. Okay, that's the minimax, and that is characterized by beautiful combinatorial quantities that's called the Vapnik-Chervonenkis dimension. So very much recommended literature for everybody who's not familiar. This is a beautiful and still very relevant theory. Okay, so but recently, instead of the excess risk, and mostly because the classes of functions that we consider lately are so big that this is essentially always zero. Okay, so we have this vast, deep neural networks that have billions of parameters. Essentially, all possible functions can be realized by this. So the question is not really basically the question how big this is just the question of how big this is. Okay, so that's why recently the focus of this research has shifted to studying the difference between the generalization, so the expected loss, and the empirical loss. So the empirical loss is nice because it's something that we can compute. This is the same thing that's computed on our data. Okay, in the old days this was called the resubstitution error. Okay, so we train our data, we train our neural network, and now we evaluate the neural network on the same data, right? The performance. So clearly, this is a biased kind of estimator of this thing, but this is what we see, and this is what we get, and we would like to understand how much worse this algorithm will do on future data as opposed to what it was trained on. Okay, this is also called the overfitting error. Right? If we use our data too much, then maybe we can drive the empirical error to be small, but the generalization error, the expected loss will be still large. So this generalization error actually kind of measures how much our algorithm overfits the data. Okay. And now these days, practitioners just train neural networks until the empirical error becomes zero, and they maybe even train it beyond that. So it would be nice to understand how big this is. Okay, right? So this is the object of our study, the generalization error. Okay, so this is just some general bullshit, and here's our first approach, right? This is the old school Vapnik-Chervonenkis type of argument. Says, okay, the generalization error surely is not larger than the worst possible difference between expectation and empirical risk and empirical risk. Okay, and if we can control this, then we can control our generalization error. So this brings everything into the realm of empirical process theory, which is a rich and well understood theory in probability theory. bounding the maximum. This is kind of uniform convergence of uniform laws of large numbers, right? So for a fixed W, the law of large numbers says that this goes to zero. The question is now if instead of just one random variable, I take a whole class of random variables, does the law of large numbers still work uniformly? And then, as I said, the VC dimension is gives us the characterization of this supremum in terms of in a distribution-free way, which is really nice, but also it has its disadvantages because it's prepared for the worst case. It's prepared for the worst case in two senses. First, it looks at the worst possible W, and it looks at the worst possible distribution of the disease. Okay, and now there was this is already more than 20-year-old stuff. Rademacher complexities offered non-distribution dependent ways of understanding this kind of maximum. So this was, for a long time, this was kind of the state of the art of generalization bound for this type of problems. But if we do this, we take the supremum over the whole class, then we lose the actual aspects of the learning algorithm, right? This is true no matter what learning algorithm I take. This upper bound is always true. So we just take the worst possible maximum. So it would be nice to understand how the algorithm interacts with the distribution in order to get real meaningful generalization bounds. Okay. All right. So indeed, there have been lots of approaches like this. One of them is called is based on the notion of stability. Stability also goes way back. The first kind of generalization bounds that used a notion of so-called algorithmic stability, even though they didn't call it like that, was in Luc de Vroij's PhD thesis. So algorithmic stability means that small perturbations of the data don't have a big effect on the outcome of the algorithm. Okay? And this can be quantified in many different ways. This is the notion of algorithmic stability. And the message in short is that if you have stable algorithms, meaning that that little perturbations of the data don't change a lot the outcome of the learning algorithm, then you can control the generalization error. Okay, so this line of work is already 2017. That's so long ago. Okay, now there's another more recent line of work. This is really specifically targeted at what's happening with deep neural networks, and this is the notion of so-called benign overfitting. So what I already mentioned is that these days very often the learning algorithm actually interpolates the data. Okay, so we just train our algorithm until the training error is zero, and classical statistics tells us that you shouldn't do this. You shouldn't interpolate the data because you're not gonna be able to generalize because of overfitting. But now, because of the specifics of the algorithm, stochastic gradient and so on, there seems that there's something there that avoids this bad overfitting, and this is called the benign overfitting phenomenon. And there are like literally thousands of papers written on this. So there's a huge literature of trying to understand this benign overfitting phenomenon for neural networks. Okay. Now our work is more in line with this newer kind of branch of generalization bounds that are based on information theoretic ideas. Okay, these are quite pretty, and they are related to the notion of stability. This we could call this information stability. For example, this bound is from this paper of Zhu and Draginsky. They showed that that if the loss function is nice, it's like sub-Gaussian. This distribution is sub-Gaussian for every W, kind of with a uniform sub-Gaussian parameter, then the generalization bound, the generalization error, remember this is the difference between generalization bound error is the difference between the expected loss and the empirical loss in expectation, can be bounded by the mutual information between the learned hypothesis and the data. Okay, so basically what it says is that if the learned algorithm doesn't reveal too much about the data in the information theoretic sense, then the generalization error will be small. Okay, so if we can make sure that somehow the algorithm doesn't memorize too much, you can't reveal too much about the data by looking at the outcome, then we can be sure that the generalization error will be small. Okay, so this is what they call information stability. And closely related to this are these so-called Pack-Bayesian bounds, which are kind of very similar in vein, but these are this Pack stands for probably approximately correct. So these don't only hold in expectation, but also with high probability, and with very concrete sub-Gaussian tail guarantees. Okay, so what this says is that for any distribution, this is kind of a Bayesian kind of framework. You take any distribution, so-called prior distribution, over the set of hypotheses. If we look at the Kullback-Leibler divergence between the conditional law of the algorithm given the data and the prior distribution, then the generalization error can be bounded by this plus something which is small. Okay, so these are the so-called Pack-Bayesian bounds, and I will come back to this after I tell you what our main ideas are. Okay, so now forget everything I said, and let's talk about online learning. Okay, so online learning is a completely different framework, and then I will show you how these two worlds come together by a crazy idea of Gergely. So online learning is a framework where a forecaster plays against nature, okay, and the forecaster tries to predict the next move of nature. Okay, so this can be formulated as a repeated game between a learner, that's a forecaster, and the environment. Okay, as Erdős used to call it, the supreme fascist. Okay, so this is a game between us and the supreme fascist, and we pick a distribution first. Okay, and then the supreme fascist selects a cost function, which can be arbitrary, just a bounded function. Okay, and now we incur this loss. So this loss is just the expectation according to our distribution of this cost function. Okay, so the supreme fascist chose this function that for every hypothesis assigns a number. Every W it assigns a real number. Let's say this is between 0 and 1. We will only consider here bounded. Well, that's not true. Okay, but just think about bounded numbers. Okay, so this is our loss, and then the environment tells us what the cost function was. Okay, and now we repeat. Okay, now our loss is just the sum of these over time. Okay, this is called the cumulative loss, and we would like to minimize this cumulative loss, but since the supreme fascist is really mean, just minimizing the cumulative loss doesn't really make sense, because the environment can always choose cost functions that are very difficult to predict. To make this meaningful, we will compare our loss, our cumulative loss, to some kind of a comparators. Okay, so there will be a set of possible forecasting algorithms, and our goal, the goal of the online learner, is to perform as well as the best of these forecasting algorithms. Okay, so if I invest in the stock market every day, I want to make money if there's somebody who can make money. If everybody loses, I'm happy to lose. Okay, but we will compare our wealth with the best possible investor. Okay, so what is this? Wrong direction. So this is what I just said. So the performance of the online algorithm is measured by its regret, and the regret is with respect to this P star, which is a comparator. Okay, and this comparator will be chosen from some class of comparators. Okay, this is the framework of online learning. I haven't shown you any theorems or any results. This is just this framework of online learning, right? So we're playing this repeated game between environment and nature, and we have our cumulative loss, and we compare it to the cumulative loss of some kind of comparator. Okay, now there are whole books written on this. I will show you the favorite one. My favorite book is this one on the subject. So there are lots of algorithms that come with performance guarantees for this type of. So one of them is the simplest kind of setup is when we only have finitely many comparators. Okay, so let's say I know that I'm gonna compete against Warren Buffett and I don't know, a small number of experts. And my goal is to have a loss which is almost as small as the loss of the best of these guys. Okay? And then what can guarantee, for example, by a really simple algorithm that's called the exponential weighted average algorithm, is that the regret, the cumulative loss compared to the best expert, is at most square root of n times the log number of experts. This is fantastic because this regret is a sum of n terms. Okay, so we can always guarantee that after n steps, we are almost as good as the best, and we lose at most this much, which is actually the best one can ever hope for. These ideas go back to Vladimir Vovk and Littlestone and Wormuth. This has a big literature in learning theory. You know, the online learning is still going strong. Okay, so here's kind of a general formalization of this exponentially weighted average method that I just mentioned. So we start with an arbitrary distribution over the hypothesis class. And at each time, when that's going to be our first initial guess, and each time when the environment reveals the cost, the cost that we suffer, we will update by multiplying by exponentially downweighting. Right? If a W had a very large cost, then now its probability will go down. Okay, and this wiggle means that this new probability distribution will be proportional to this, properly normalized so that it's still a distribution. Okay, so this is the exponentially weighted average forecaster. It's really simple, and what one can prove is in just a few lines is that the regret is bounded by the KL divergence between. So for any p, this is true no matter what this comparator is. This is going to be bounded by the initial KL divergence between the comparator and our initial distribution divided by eta plus eta and divided by 2. And you can see if you choose eta to be something like 1 over root n, then this is where the root n scaling comes in. Okay. This is very simple to prove. In a few lines, you can show this. Okay, so this is this is kind of a general formalization of the exponentially weighted average forecaster. So here's where our two worlds come together. Okay, this is Gergely's idea. Generalization gain. So we will consider a very specific online learning game where the cost, remember, in our original statistical learning problem, we had these data, this IID data, and we are learning this W. Okay, so the generalization game is this online learning game where the cost is just the loss, the cost associated to a W. This is just some fixed neural network. Is the loss minus the expected loss. That guy. Okay. This is a zero mean random variable for every W, right? And that's the cost. It's a complicated function. It depends on the loss, depends on the distribution of Z's and so on. It's a really complicated thing. And the online learning game, sorry, the generalization game is just an online learning problem using these costs. It's nothing else. Okay. So the online learner picks a distribution, right? Now the environment selects this cost function, which is the loss centered, and then the loss of the online learner, the cost of the loss of the online learner is just we use this inner product notation. It's just the expected value of the cost with respect to the chosen distribution, and then the environment reveals the cost function. Okay, so this is our game. Okay. Now, in this game, we have regret bounds. Okay. All right. So this is the main idea is on this slide, and you see this is my advisor used to say that equality is engineering, inequalities is mathematics. So this is an engineering slide. Okay. There's nothing here. It's a physics, yeah. I come from engineering, but I guess it holds for physics as well. So what we study is the generalization error. Okay, and we write this upper bar because we take the expected value with respect to the internal randomization of the algorithm. Okay, so if you want to think about deterministic algorithms, then the generalization, this gen bar is the same as the generalization error. Okay. All right. Now take any online algorithm. It can be as stupid or as smart as you want. Any online algorithm. For any online algorithm, this slide is true. So by definition, this is the generalization error. It's just the expected loss minus the empirical loss. Yeah. Which, because of the definition of this online learning game, this is just CT. The CT is just the difference between it's minus CT. Okay. Good. And now I will add and subtract the same thing, which is the cumulative loss of PT. Of the PTs are just the distributions that's output by this fixed online algorithm. So this is just the performance of our fixed online algorithm. And then what we observe here is that this first term is just the regret of this online learning algorithm with respect to this particular comparator distribution. Okay, this comparator distribution is just the conditional distribution of Wn, which is the learned hypothesis given the data, minus the performance of this algorithm. So the generalization, this is an equivalent. We rewrite equivalently the generalization error by introducing an online learning algorithm. Okay, any online learning algorithm. Now, the funny thing here is that this last term is zero, essentially. So this last term is just the sum of bounded martingale differences. This is a zero expected value thing by very simple martingale inequalities. This is at most of the order of 1 over square root of n. Okay, so this is peanuts. This doesn't matter. The only thing that matters is this regret. Okay. Okay, so the generalization error essentially equals the regret of what? Of an arbitrary online learning algorithm, where the regret is computed with respect to the best, with respect to the probability distribution that our algorithm outputs. Okay, so how do we get upper bounds for this? Well, if I can bound the regret, then I will have a bound for the generalization error. Okay, but the whole theory of online learning is about this: finding regret bounds for online learning algorithms. So now what we will do is that we will choose this Bayesian, this online learning algorithm, such that we can control this regret. Okay. This is really weird because, as I said, this equality here is, of course, this depends on the online learning algorithm, but in a really mild way, because this is always, for any fixed online learning algorithm, this is just a martingale, which can be controlled in an easy manner. Okay, so here's what we get immediately. If our loss is well behaved in a mild sense, all we need is that the second moment of the losses are uniformly bounded. Then, with probability at least 1 minus delta, the generalization of any learning algorithm will satisfy this inequality for all possible learning algorithms. The generalization error is bounded by the regret of that learning algorithm plus peanuts. Okay? So what this says is that in order to show that the generalization error is small, all we need is to exhibit the existence of a good online learning algorithm. Okay? By good, I mean that whose regret is small. Okay, so let's try to wrap our head around this. So first of all, clearly, because this is true for all online learning algorithms, these online learners don't actually learn. Okay? The cumulative loss of this online learner, since as it's a sum of zero mean martingale differences, this is small. This is at most of the order of root n. Clearly, because we cannot predict. We cannot predict. These are IID. There's no way of meaningfully predicting independent, identically distributed values. So all online learners perform essentially equal. So the reason the regret is small has to be because the comparator is also bad. Because this algorithm, and what is this? This algorithm is our learned algorithm. So what this says is that if our learned algorithm is unable to predict the actual training samples, then the generalization error is small. Okay, so the regret can only be small if, since the learner has a trivial cumulative loss, the regret can only be small if actually the comparator is really bad as well. Okay, and the comparator is bad. What that means is that the learned algorithm cannot predict the data. Okay? Which is all right. This is intuitively fine. If the algorithm doesn't remember our data, then we expect a good generalization. Okay? So this can be now we can okay. Let me skip this. I'm gonna skip a lot of things because it's late. But now we can plug in our general bound, we can plug in known online learning algorithms, and we will see what we get. Apply the known regret bounds and see what we get. And it's interesting that we get something. For example, if we use just the exponentially weighted average forecaster in its vanilla form that I showed you, then we immediately recovered the Pack-Bayes inequality without work, which was proved in a completely different manner. That was one of the generalization bounds that I showed you before. And if we use a little bit more advanced results from online learning, recent results about parameter-free algorithms, then we can actually improve the Pack-Bayes inequality by removing some unnecessary log-log factors that were always there. Okay, so what we can get is that just by plugging into this result this particular online learning algorithm, what pops out is that the generalization error is bounded by, and this is exactly what we had in the Pack-Bayesian upper bound, but with some, the small term is a little bit better than before. Okay, so this already gives us something. We can also now once you have a proof, you can find many theorems to that proof, right? That's usually mathematics. Find the proof, and you have 100 theorems. So the next theorem is that we can modify a little bit our cost function and add this kind of regularization term to it. Now, if you do that, this is not the sum of these costs is not a martingale anymore, but it's a super martingale, and then we can get using again ideas from the theory of online learning, we get this kind of data-dependent bounds. The generalization error is bounded by, now this is kind of the quantity that we get in the Pack-Bayesian bound, but now we have another term which has the losses of the learned algorithm inside. And in particular, if our algorithm interpolates and the losses are zero, then this term disappears, and what we get is a much faster rate. Then we can choose this eta to be a constant, and what we get is, before that we had this with a square root. Now the square root goes away, and we have fast rates. Okay. What else? So another. Okay, let me just very quickly say that another big class of online learning algorithms is the so-called follow the regularized leader algorithms. So follow the leader would be always choosing the probability distribution that looks best on the past costs, right? We always choose the best in hindsight. That cannot work because of the supreme fascist. It's too powerful. But if you regularize, and this regularizer is a convex function on the class of probability distributions, that is actually a little bit more than convex. We need it to be strongly convex with respect to some norm over the set of probability measures. And this is what strong convexity means. So this would be convexity, but now we require of the addition of this quadratic term. So if you regularize by a term like that, then we can get generalization bounds in terms of that regularizing function, and here the dual norm of the norm that was used in the definition of the strong convexity of H appears. Okay, and now you can start playing. And since I don't have time, let me just show you just one bound that we get, which is new as far as I know. So here we're using a kind of smoothing of the relative entropy as a regularization function, And what we get is that under the only condition that the loss has finite second moment, we can bound the generalization error in terms of the Wasserstein distance between, this is the L2 Wasserstein distance, between the learned probability distribution and the prior distribution. So this is a new, we get a whole new class of generalization bounds of the Pack-Bayesian style, always just using online learning ideas and before this game, okay? So I'm gonna stop here. There are other variations of this and just give you a few ideas that I would like to work on, we would like to work on. So this is the main takeout, that this generalization game gives us a whole toolbox we can now use the whole theory of online learning to get generalization bounds using this simple but strange idea. What is still missing is that we don't have killer examples where we can. So all these Pack-Bayesian bounds, they say that if the learned distribution has a small distance to some kind of prior distribution, then we are fine. Okay, but how can we? Is it possible to tailor our online learning algorithm to the statistical learning algorithm? Because all these applications, these were completely decoupled. We just take online learning algorithm that comes with regret guarantees that are universal, that are for in the worst case. But maybe we can use, we can design new online learning algorithms having the knowledge of what we are trying to learn. Okay? We don't know how to do that yet, but I think this could be very interesting. It would be nice to see if we can frame all this previous work, benign overfitting and so on, in this kind of framework. And another thing that could be interesting is because you remember the engineering side, that was all equalities. So in principle, we could also use this framework to prove lower bounds, impossibility for generalization error, to show that the generalization error has to be large. And for that, all we need to do is to exhibit a learning algorithm that has a large regret. That has a large regret. Okay? So these are possibilities for future work, and I won't hold you for longer. Thank you.